So in this chapter we will study martingales, and the chapter will consist of 3 sections. So in the first section that we discuss in this video, we will give a definition of martingale and consider some examples. And toward the end of this section we will also discuss some technical preliminaries that we will need later on. Okay, then in the next 2 sections we will discuss several of the most famous aspects of martingales. So in the second section we will discuss stopping times first. Okay, and then we will prove this very famous result called the optional stopping theorem. And toward the end of the section we will also apply this optional stopping theorem to get a few results on random walks. Okay, and then in the last section we will first discuss some inequalities for martingales, and then toward the end of this chapter we will discuss convergence of martingales, several theorems about convergence of martingales. And already in this video we will preview some of these convergence results in the context of the examples that we will give. Right, so let's start now with the definition of martingales. So we consider some probability space omega with sigma algebra B and some probability measure P. And we'll also have an index set that will index our martingale. So this will be a linearly ordered set. So the set will be T with a linear order. So this will be a linearly ordered set. Okay, which typically will be a subset of the real line. In fact, in this chapter we will mostly focus on sequences. So for example, this will be simply a subset of, let's say, integers, such as natural numbers, okay, with the usual order. And then we will have this process which will be just random variables defined on this probability space indexed by the points in this set T. So okay, so we'll have this sequence, or not the sequence, but we'll have this family of random variables on the probability space, real valued, and so the index T here will be from this index set T. And we will also have some family of sigma algebras that will be denoted BT, and these sigma algebras will be sub-sigma algebras of the sigma algebra on the probability space. Okay, so here this xt will be random variables and BT will be sigma algebras. Okay, moreover, the sigma algebras will be increasing in the sense that if you take 2 indices t less than or equal than s, then the sigma algebra BT will be inside of BS. This family of sigma algebras will be increasing. And so in some places, we will emphasize this, but by default everywhere in this chapter when we talk about this family of sigma algebras, this increasing assumption is always there, okay, by default. So now let's give a definition of a martingale, in particular when this family of random variables and sigma algebras form a martingale. Okay, so the definition is the following, that this family of random variables and sigma algebras indexed by T in this linearly ordered set is called a martingale if the following several conditions hold. So first of all, xt is assumed to be measurable on the sigma algebra BT, or with respect to the sigma algebra BT. So xt is BT measurable. Okay, it's also called adapted. So we also say xt is adapted to BT. Now the second condition is that all these random variables are integrable. So the expectation of the absolute value is finite for all indices t. Okay, and again, in some places, when we don't check this condition, it either means that it's obvious or easy to check, or it's implicitly in the proof. Now, the last assumption is really what defines the martingale here, namely that if you take two indices t and s is the bigger one, so then the conditional expectation of xt given sigma algebra bt should be equal to xt, okay, for any pair t less than or equal than s in our set. Okay, this is really the key assumption, what defines a martingale. And it just means that you have this sequence of sigma algebras, or this family of sigma algebras that contain some data. So typically, for example, they will be simply sigma algebras generated by the random variables xt themselves. But when you take an average of some of your process xs at some future time s, conditionally on the data that you have at time t, you simply get the process at time t. So for example, this will model the so-called fair games, that if you think of a sequence as some kind of game, then given the information that you have at any given time t, the value of this game at a future time cannot be greater or smaller than on average, conditionally on what you know now. So conditionally on the sigma algebra bt, the value of the process at a future time must be equal to its value at this moment. Now, if you want inequality here, this also has a name. So if inequality is in this direction, then this is called sub-martingale. In other words, the value at a future time on average, conditionally on the present, is greater or equal than the value at the present time. So, your process on average is increasing in this sense. And if it's the other way around, this is called super martingale. All right, so this is the definition of a martingale and sub-martingale, super martingale. So let's give a few examples right now. Okay, so let's start with the first most basic example that will also come back in the next section, which is just a random walk. Okay, and here we simply consider a sequence xn of independent random variables on our probability space. And the index set here is just natural numbers. So we consider a sequence starting from 1 or from 0 of these independent random variables. And we assume that their expectation exists or is well defined, and moreover it is 0. So these are all centered. And then we look at the sum. So Sn will be the sum of this first n random variables xi. Okay? And Bn will be simply a sigma algebra generated by this sequence up to time n. Okay, then this pair Sn Bn is a martingale. Okay, so the first two properties are just by definition and by assumption. So the sum is obviously measurable with respect to the sigma algebra generated by x1, xn. And we also assume integrability. So we only need to check this last property, that if you take two indices m less than or equal than n, then expectation of the sum at a later time n, conditionally on the sigma algebra generated by x's up to time m, will give you a Sn. And of course, if you simply write the sum up to time n as the sum up to time m plus the random variables x m plus 1 up to x n, then what we want really just follows from the properties of conditional expectations, right? Because Sm is already measurable with respect to Bm, so conditional expectation is just Sm itself. And then, because xi's from I starting from m plus 1 are independent of the xi's which generate Bm, right? We also have this property that when you have independence, the conditional expectation is just equal to the expectation. So the sum from m plus 1 to n by independence, the conditional expectation will be just the expectation of these xi's, which are all 0, so you get Sm almost surely. Okay. Now, if the expectation would be positive, this would give you a sub-martingale, and if it's negative, you would get super-martingale. All right, so that's one example, maybe the most basic, but some of the interesting results that we'll discuss in the next section will be in this setting. Now, let's take a look at the next example of the so-called right closable martingale, which will be, in some sense, a quintessential example of the martingale in this chapter. So first, let's give a definition. So what right closable martingale is the following: that you have this family of increasing sigma algebras in your probability space like before, and then you consider one random variable x on your probability space, which is integrable, right? And this random variable defines your right closable martingale. So by definition, then you take xt to be simply the conditional expectation of this random variable x given sigma algebra bt. Okay, so that's the definition of this right closable martingale generated by a given random variable x. Okay, so of course, by definition of conditional expectation, this is adapted to bt, so this is bt measurable. Now, integrability just follows from conditional Jensen's inequality, that if you put absolute value here, you can take absolute value as a convex function inside the conditional expectation, right, by increasing, so by this equality becoming inequality. And then if you take expectation of both sides, you see that in the sense of L1 norm or the integral, this random variable x controls all random variables xt that it generates, right? So this entire process is not only integrable, but the expectation or L1 norm is controlled by the L1 norm of x. And finally, the last property, again, it's just a property which we call the smoothing property of conditional expectation. That if you take a time s greater or equal than t, then you take conditional expectation of xs given sigma algebra bt. Well, here by definition, xs is just conditional expectation of this random variable x given sigma algebra bs, right? And then you average on the sigma algebra which is inside bs, and that's what we call the smoothing property, that if you average in two steps, it's the same as averaging in one step. So that's the same as conditional expectation of x given bt, which is the definition of xt. Now, it's called right closed if this random variable x is part of your index set. So it's indexed by some t in your index set t. So we'll say that your martingale is right closed if this random variable x is also indexed by some t naught, which is an upper limit. So it's, it's one of the indices in our set which is bigger than all other indices. Of course, if it's not included, if x is not indexed, you can simply close your martingale, right? You can always add an additional point at infinity and simply index this x by, by this additional index at infinity. So a right closable can be right closed, but we'll keep this distinction in the notation or in the terminology. Okay, so one reason why I said that this will be a quintessential example is that one of the most famous and most important results on convergence of Martingale sequences will say that, okay, so let me maybe give this as a preview of one of the results that we'll prove later on, namely that all uniformly integrable. So we'll discuss this later in this section, what uniformly integrable means, but all uniformly integrable martingales or martingale sequences xn, bn are right closable. Okay, that will be part of the first of all, xn will converge almost surely, and the limit will be the random variable that generates the whole sequence. Okay, so of course this uniform integrability assumption that we'll discuss a little later, in some sense it's a strong assumption. But if you have this property of uniform integrability, then your example or your martingale sequence must be of this form as a right closable martingale. So let me give maybe one kind of fun example to illustrate these right closable martingales and this convergence theorem. So if we take a look at this picture here, we can think of it, so our probability space here is just a, let's say, 1 by 1 square with the back sigma algebra and uniform probability measure. And the function here is just the pixel value of this image, right? So at every point you have, this is a grayscale image, so you have just one number describing the value of the function, right? Now, the way we can turn this into a martingale is the following. So we can consider this sigma algebra generated by these 9 rectangles. And then if you think of this right closable martingale, all we did here is we took the values of this function on a given square and we averaged them, right? So the first function in this sequence is just the average of the pixel values on each of these 9 squares. And then for this to be a martingale, you have to refine your sigma algebra. So for example, you can split each of these squares into 4, and then you can average your function or your image on those squares, right? And then you can keep going. You can split those into 4 again. Right? And so this kind of sequence where you refine your sigma algebra by splitting the previous squares into 4 will form a martingale if you keep averaging the values of this image on those squares. Okay, so that's an example of right closable martingale. In the other direction, if we think about this convergence theorem, what this means is the following: that a priori you don't know that there is this image that we are averaging. So all you see is this sequence, and you can check that it is indeed a martingale. When you go from this step to the next, your sigma algebra is refined, and you can easily check that if you take the values of this function on this more refined sigma algebra, so in other words, if you take any 4 squares that formed a bigger square at the previous step and you average their values, you would get the previous function, right? So you can just check that this last condition is satisfied. And then at every step you can see that the sigma algebra is refined, and you can check that the average of the values of the four smaller squares inside the previous bigger square will give you exactly the previous function, right? And so if you do that, you can ask yourself, will this process converge? Because you can imagine, of course, that at some point something that starts looking like a cat, at the next step maybe it will look like a dog. Okay, so maybe you can come up with a clever example of this pixelation where there is some oscillation going from one step to the next. That maybe you can construct something that is a martingale, but it keeps oscillating. But this result that I mentioned, that all uniformly integrable martingales must converge, means that you cannot actually do this forever. So eventually, when you keep refining your functions on the measurable with respect to those sigma algebras, will have to converge to some limit. They cannot keep oscillating. And in the setting of images, this uniform integrability will be obviously satisfied because our function are just bounded here. The sequence of images is just bounded. Okay, our next example is not really a new example, but I just wanted to remind that we have already seen this averaging process in the first chapter when we discussed Azuma inequality. We mentioned at that time that the representation that we constructed is called Martingale difference representation. Okay, so in Azuma inequality we considered some random variable which was given as a function of n random variable xi1, xin. And so what we did is we consider sigma algebra, so B0, which was just a trivial sigma algebra, and then sigma algebra Bm for m from 1 to n. It was a sigma algebra generated by this random variable xi1 up to xin. Okay, so it is an increasing sigma algebra because we keep including some random variables, and then we consider the averaging procedure just like in the previous example, where we define a random variable which is the average of our function, so the average of this random variable x, conditionally on the first m random variable, so conditionally on this sigma algebra Bm. So it's exactly the example as above, only we have finitely many indices. And if you take a look at the last one, right, because the random variable x is itself measurable on the last sigma algebra, you don't need to average, so xn is just x, and x0, when you average with respect to the trivial sigma algebra, you must get a constant, so this was just the expectation of x. Okay, and then we wrote this representation using the telescopic sum, that if you start with the index 0, so this expectation of x, and then you take a sum over m from 1 to n of these increments xm minus x m minus 1, right? You will recover the last one, which is exactly x. Okay, and so we call this a Martingale difference representation exactly because this sequence xm forms a martingale, and we look at the sum of their differences. So in particular, if you look at this increment here, you can see that it's a Bm measurable. And then the property that we used in the proof of Azuma inequality, that if you take expectation of this increment conditionally on the previous sigma algebra m minus 1, you will get 0. So these were centered. But in any case, this is just a reminder that we have already seen this type of construction before. Right, and the next example, okay, which will be the final example here, is the so-called reverse martingales. And this will give us a new point of view on the strong law of large numbers, or a new proof of the law of large numbers later on. So particularly here, we start by looking at IID sequence. We have xi indexed by these integers, which will be independent, identically distributed, integrable, and Sn will be the sum of x's from 1 to n. Now here we do not assume that they are centered, so the expectation is 0, because we don't just look at Sn as we did in the first example, where we needed the expectation to be 0 for this to be a martingale. So here something really clever is going on in this new construction. In particular, the index set, surprisingly, it will not be just our natural numbers from 1 to n and so on. This will be actually minus the natural numbers. So this will be the negative integers ending at -1. And the sigma algebra be indexed by this negative integer -n. It will be a sigma algebra generated by the sum Sn and all the future sums. So Sn plus 1, Sn plus 2, and so on. You can also just take the first sum, and then of course if you know all the future sums, you know the values of xn plus 1, xn plus 2, and so on. So these are equivalent definitions of the sigma algebra. Notice that with this definition, you do have inclusion with the usual order on the integers. That if you go to, if you take one step to the left, you go to minus n plus 1. In your definition, you exclude the first sum. So that's a sigma algebra generated by one less sum, so it becomes smaller. So it is included in the sigma algebra b minus n. So you have the increasing property with respect to the usual order on the integers. And then we will consider this right closed martingale, where the random variable z minus n will be just the conditional expectation of the first sum, which is just x1, conditional expectation given the sigma algebra b minus n. So again, it is a right closed martingale in this case, right? In particular, what is z minus 1 here? Just an expectation, conditional expectation of x1 given the very first sigma algebra, which is generated actually by x1. So z minus 1 is just x1. Right, but now we have to notice what is this z minus 1. Well, if you calculate this conditional expectation, or if you take a look at this conditional expectation given the sigma algebra generated by Sn, and then xn plus 1, xn plus 2, and so on. One of the properties of conditional expectations that we discuss is this property of conditional independence, that actually, in this case, all of these random variables starting from n plus 1, they are independent both of x1 and of Sn. So x1 and Sn are not independent. I mean, x1 appears in Sn, but all these other ones starting from n plus 1, they are actually independent. So you can omit them in this condition, right? So it's the same as conditional expectation of x1 given just Sn. You can notice next that when you take conditional expectation on this right hand side of x1 given just the sum Sn. It will be the same as conditional expectation of any other xk given the sum if you take any index k from 1 to n. So intuitively this is clear just by symmetry, right? Because x1 up to xn, they are all identically distributed and independent. So when you fix their sum conditionally on that, it doesn't matter which one of them you average. But of course, it's important to take a look at the definition and prove this carefully, which is left as an exercise at the end of this section. But once you notice this, then you can also write this conditional expectation as the average. Since they are all equal, it's also the average of all these conditional expectation indexed by k from 1 to n. And by linearity, you just get conditional expectation of the sum divided by n. Okay, and because the sum is measurable with respect to the sigma algebra generated by the sum, this is just Sn. So what this shows is that it's Sn over n. So what this shows is that z minus n is nothing but this average that we look at in the strong law of large numbers, right? So Sn over n and the sigma algebra b minus n, this is a martingale indexed by this negative integer, so indexed by minus n less than or equal than minus 1. So you look at the negative n as the index here. Okay, so this is a martingale. And when we prove the results about convergence of martingales, this example will give us a new proof of the strong law of large numbers, because we'll see that this Sn minus n, Sn over n must converge when you let this index go to minus infinity. All right, so this covers all the examples, and in the remainder of this section we'll discuss some technical conditions that we'll need actually in the last section when we discuss convergence of martingales. So namely, here we'll discuss this uniform integrability that I mentioned above. Okay, so the definition of uniform integrability for a family of random variables is as follows. So we'll say that a family of random variables xt indexed by some index set t is uniformly integrable if the following condition holds. Namely, if you look at the integral of the absolute value of t on the set where this random variable is large, so on the indicator that xt is greater than m. Now, we know that if xt is integrable, then just by monotone convergence theorem, this would go to 0 when m goes to infinity, but we require this to be uniform over the index set. So if you take supremum over all t, then this should still go to 0 as m goes to plus infinity. Okay, then if this occurs, then the family is called uniformly integrable. So in other words, kind of the part of the integral of our functions in the tail is uniformly small. All right, so as a motivation here, I wanted to first start with this lemma about right closable martingales, something that I have already alluded to before. Right, namely, we have the following result, that if our martingale is right closable, then it's automatically uniformly integrable. Okay, and let's call this 1 because we'll also need a similar statement for submartingales. So namely, if a submartingale sequence which is right closable, then the truncation from below is uniformly integrable if you truncate from below at any real value a. Okay, and in the first statement here, I of course meant a right closable martingale. And in the second statement, well, what do we mean by a right closable submartingale? We mean the same statement as for the martingale, that except with an inequality, right? That xt is less than or equal than the expectation of some fixed random variable x conditionally on bt. So it's just like the inequality in the same direction as what you see for in the definition of submartingales, but here you also have this control by the average of one random variable. Okay, so you have this plus, of course, the definition that this is submartingale. All right, so let's take a look at the proof, and of course the proof is going to be pretty straightforward because you have this one random variable that defines everything, so everything will be controlled by one random variable. So we have already seen that because for right closable martingale the definition is just this conditional expectation, right? We have already seen that if you take the absolute value by conditional Jensen's inequality, this is bounded by conditional expectation of absolute value. So that implies that this random variable x controls the L1 norm of the whole process. But here we want a little bit more, namely we want to look at the average of this absolute value on the tail when absolute value of xt is large. Okay, but what we'll start with is exactly the same observation here, that the absolute value can be bounded by this conditional expectation. So we'll use this first and replace this first xt by this conditional expectation. Okay, and we'll leave the indicator as it is. All right, but now we'll notice that xt is measurable with respect to bt by definition of the martingale. So this set here, xt, the absolute value of xt greater than m, of course it's in the sigma algebra bt. So by properties of conditional expectation we can take it inside of this conditional expectation, and we can write this as the expectation of conditional expectation of absolute value of x times the indicator. Okay, which of course conditional expectation and then taking expectation just gives you the expectation of this absolute value times the indicator. Now, if you remember that an integrable function is uniformly integrable in a sense that if you integrate over indicator of some small set, it doesn't matter where that set is located, the integral will still be small. And if you look at this set here, you can easily notice that its probability is small no matter what the index is, right? Just by Chebyshev's inequality. Right? If you use Chebyshev's inequality, this is bounded by expectation divided by m. And we already control all expectations uniformly by expectation of x. Right? So you can make it as small as you like, so by choosing m large enough uniformly for all t. And so this gives you that this expectation that we want to control is small uniformly for all t, because it doesn't matter where, what this small set is. Now, of course, we can just repeat the proof, how the proof of that statement would go, by splitting the integral. So the integral above here, let's split it into two sets. So let's take one set where a random variable x is bounded by some large constant k and its complement when x is bigger than this large constant k. Then on the first set we replace x by k. So x is bounded by k, so we replace it by k, and we are left with just the indicator. So the average will give us this probability of the tail, right? And then on the second set, when x is greater than k, well, we don't touch the x. We simply write the indicator that x is greater than k, and we throw away the indicator for about x. We throw away this indicator with xt. Okay, and now we just observe what we wrote above, that this probability can be bounded by Chebyshev's inequality uniformly over all t. And so the index t now disappeared in this upper bound. So in particular, if you take a supremum, so what did we start with? We started with this expectation over the tail, and we want to control it uniformly. So if you take supremum over t on the left hand side, and you take the limit when m goes to infinity, on the right hand side the first term will disappear when m goes to infinity, so you'll be left with just this expectation of x over its tail. Okay, but this is true for all k, so now when you let k go to infinity, this will go to 0, and that proves that this limit here is 0. Just like we wanted, so this proves a uniform integrability of right closable Martingale. Now for sub-Martingale, I'm not going to go through the whole proof. It's very similar, so I'll just leave it to the notes, but I'll just make one quick observation in the very first step. Namely, what we have is that xt is bounded from above by this expectation of some random variable given bt. So we do not have equality here, and in particular we cannot take the absolute value because we only have control from above. Right? The absolute value will not necessarily have the same inequality. And for this reason, we use the truncation. So we take some real value a, and we take truncation from below by this value a. Right? And if you take a look at how this function looks like, in addition to, so it's a up to a and then x after that, right? So it looks like this. So in addition to being convex, it's also non-decreasing. So when you apply the truncation, you can use this condition here that the maximum, so the truncation of xt from below will be less than or equal than the truncation of this conditional expectation by monotonicity, but then by convexity you can also combine it with Jensen's inequality and take the truncation inside. So you will have such inequality here, and as a result, if you take expectation, you will have uniform control of the expectation, at least for the truncations. Okay, now of course you want to apply absolute value and you want to look at the tail for these truncations, but this is very similar to what we did in the case of the Martingale, so I'm not going to repeat the proof again and just refer to the notes for the rest of the proof. But I wanted to emphasize here is that the reason we have to take truncation from below is because we only have this partial information. We have partial control by this random variable x from above, but not from below. So we have to control from below by truncating. All right, so this shows that a right closable martingale must have this uniform integrability property, and as I mentioned before, in the last section we'll prove the reverse statement, that if a martingale sequence is uniformly integrable, then it must be of this form. It must be generated by one random variable just by averaging it with respect to the sigma algebras. Now, finally, I wanted to mention another technical result which will be useful to us in the proof of convergence, and this is a certain generalization of the dominated convergence theorem, or some relaxation of the dominated convergence theorem. Okay, so namely, suppose that we have a sequence of random variables which are all integrable, and we have some random variable x which is also integrable, then the following are equivalent. Okay, so one is the convergence of xn to x in L1 norm. Okay, so if you take expectation of the absolute value of their difference, this goes to 0 as n goes to infinity. And 2 is that this sequence xn is uniformly integrable plus xn converges to x in probability. Right, so the usual dominated convergence theorem would ask for xn to converge to x in a stronger sense almost surely, and then if you have a domination by one random variable x from above, of course the whole sequence becomes uniformly integrable. But here you do not require almost sure convergence, you just ask something weaker, convergence in probability, and you just ask uniform integrability instead of domination by one integrable function. Okay, and again, the proof in one direction here from 1 to 2, it's very similar to what we already did, so I'll just leave it to the notes and only quickly discuss how the proof goes in the direction from 2 to 1. Right, so if we assume uniform integrability and convergence in probability, how do we get L1 convergence? Okay, so, well, this is done as follows. So when you look at this expectation, first you break it into two pieces when the difference is less than epsilon and bigger than epsilon. So on the first piece you just bound it by epsilon, and so on the second piece we put indicator that this difference is bigger than epsilon. Then for this second integral we consider several possibilities. So one possibility is that both xn and x are bounded by some large constant, and another possibility is one of them exceeds some large constant k. So it's also in a way very similar to what we just did a second ago. So on the set where both of them are bounded by k, the difference is bounded by 2k. So we will be left just with this average of the indicator. So this will give us probability that xn minus x is greater than epsilon. Okay, and our assumption is that this probability goes to 0 as n goes to infinity, because xn converges to x in probability here. This term will go to 0. And then we have another possibility that the difference, not the difference, but the absolute value of one of them is greater than k. Well, that possibility we can also break it into two pieces. Which one is bigger of the two? So in one case, let's say x is bigger, the absolute value of x is bigger than absolute value of xn. Okay, then the difference will be bigger than twice x, right? And since we assume that one of them is bigger than k and x is the bigger one, well, that means x is bigger than k. Or another possibility that xn is bigger in absolute value. Well, then the difference is bounded by twice xn. And again, the indicator that one of them is bigger than k means that xn is bigger than k, because it's the bigger of the two. So we can, and in both cases, we just omit the indicator that we had before, right? And so that just increases, because we are integrating positive functions here. And then the last term here, that's our assumption of uniform integrability. That even if you take a supremum over all n, on this side, this will go to 0 when k goes to infinity. So you can take k large enough such that the second term is as small as you like. And of course, here, because x is integrable, you also, by monotone convergence theorem, this can be also made as small as you like when k is large. And so as a result, when you let n go to infinity, the limit on the left hand side, so this L1 distance between xn and x, right, it will be bounded by epsilon plus two terms that you can make as small as you like. So that means it will be 0, just like we wish. Okay. And then in the other direction, 1 to 2, I'll again refer to the notes because it's very similar to what we did in the lemma about right closable martingales. And so this concludes the overview of these technical results about uniform integrability that we'll need later on, and this also concludes the first section of this chapter.